Hi, my name is Tyler Williams, and this is a presentation on the thin layer electrochemical sensor that we're developing for molten salt use. And this presentation was originally given at the fall meeting of the American Chemical Society in 2024. So the reason why we're interested in a thin layer is a thin layer electrode holds a very small amount of solution right next to an electrode. And the amount of solution that we're holding right next to the electrode weighs about as much as an ant, is about 10 times thinner than human hair, and can diffuse across that layer in the blink of an eye. So, but why really do we want a small gap? It's because once you start trying to make electrochemical measurements at high concentrations, the models that we have developed for diffusion-only mass transfer start to break down because then we have migration and convection. So the solution is, like I said, you hold an insulating layer very close to an electrode. And when you do this, you get behavior that approximates having an adsorbed reactant, where your reaction is only dependent on thermodynamics and kinetics and not on mass transfer anymore. So some of the benefits for this is we can measure both low and high concentrations of our analyte. We have narrower peaks, which helps us to analyze samples that have multiple analytes inside with similar reduction potentials. And developing this technology will lead eventually to us being able to do spectro-electrochemistry at the surface of our electrode, getting a lot of information about the mechanisms of these reactions and how they're going on. The orientation for our setup is, we have a tube furnace in a vertical position, and we insert our thin layer electrode. We have a quasi-reference electrode that we're running with for these experiments, the data I'm presenting today, and a counter electrode. And all of these are being placed into a salt bath. Now, if we flip the thin layer electrode on its side, then you can see a few key components. We have the extender that helps bring the apparatus down into the furnace. We have the electrode that goes through the extender and mates with the receptor. And the place where they meet is the thin layer, and that's where the thin layer of solution is. There's also a pinhole leading from outside of the receptor to that thin layer so that we can pull in samples and push out the solution that we've already measured. We've made these so far out of a few different materials. So Pyrex and quartz we've made them out of, and we've tested them with Pyrex multiple times. These are great in chloride salts, but in fluorides, they have they're not chemically compatible with fluoride, so we can't use them there. You can't really machine these too easily, so you have to have a glass blower make them for you. There's some ion permeation, which is handy for good electrochemistry measurements. And the biggest benefit is that they're transparent. So as we continue to develop these technologies, eventually we'll be able to do spectroscopy with these glass receptors. The ceramic receptors are our main workhorse. So boronitride and boronitride, aluminum nitride, these are ion permeable ceramics. They're machinable, but they're opaque, so they're not a candidate for spectro-electrochemistry, but we can use them in chloride and fluoride salts, so that's a large advantage for us. And finally, we're in the process of developing some metal receptors. We're making them out of tungsten, and we'll see how they go. We'll be receiving them from the machine shop sometime soon, and then we'll be able to test them out. So if you were to go this next week and build your own thin layer electrode for molten salts, and I hope you do, the first thing you need to think about is how big of a pinhole do you want. And And to help us make that decision, we decided to model the amount of leakage current is what we're calling it. It's current due to ions traveling through our pinhole and into our thin layer solution during our measurement. So all the thin layer relations that you'll find in textbooks, those assume that nothing is traveling inside. But the trick is that we need the pinhole so that we can flush out our solution, pull in more solution. And if you don't have an ion permeable receptor, then you need it so that you can have electrochemical communication between your electrodes. So we approximate the current flowing through. We say it's the current that a similarly sized ultramicro electrode would experience. And so for our process, having a 1/64th inch pinhole introduces, we believe, around 1% error. Next thing you need to consider is flushing and sampling. So in our process, we need to be able to do both and to do both consistently. We started off our process with a baby bulb because I'm a new father and that's what we had on hand. And since we've upgraded to a syringe so that we can be more precise. You can see if you get flushing right, then you can pull in a lot of solution as well as pull it out. It's very important that we can flush and sample consistently. The next thing we need to talk about is impedance and ion permeation. So these numbers are included here just so you can get a scale of an idea of the size of our system. So 0.02 millimeter thick thin layer, a pinhole that's about 0.4 millimeters, and then a receptor that's around 28 millimeters thick. Why would we want an ion permeable receptor? So something like the boronitride instead of the glass. Well, it's because the more ion permeable your receptor is, the easier it is ions have traveling through it. And what you end up doing then is you have a consistent electrochemical environment inside of your thin layer for your electrochemical measurements. If you have an ion permeable membrane, then your ions have to travel all the way through here, including some very narrow sections, and those narrow sections lead to a high amount of resistance in your measurements, and that resistance then leads to a voltage drop, so you have a really different electrochemical system here at the bottom part of your electrode than you would at the top of your electrode. So you can measure this. Here's a measurement we made over 12.5 hours as we put a boronitride aluminum nitride receptor containing its electrode into a salt, and then took electrochemical impedance spectroscopy. And here's the Nyquist plot for it. You can see that originally it starts off vertical, and then as the time goes on, our curves slowly start to curve over and make that semicircle shape. That's indicative of the resistance dropping through our ceramic. So here's the circuit model that we're using. We have a capacitance through our receptor. We have a ceramic resistance that'll decrease as ions permeate into it, and then a solution resistance outside. So when we modeled our data, fit our parameters, then we saw that the ceramic resistance dropped orders of magnitude over this 12.5 hours, while the solution resistance and the capacitance through our receptors stayed fairly constant. So on to some more data. So here are some CVs. This is a borosilicate receptor with a large pinhole in chromium chloride. So you can see that the CVs, they have these bell shapes, but the look of them is something between a normal Randall Subchik curve and a ideal thin layer electrode curve. We believe that that's because we have a large pinhole. So there's a component of the current coming through the pinhole that would make it look more like a Randall Subchik curve. but then the solution in the thin layer, that's creating more of these bell-shaped curves. The nice thing though is that even with that leakage current, we can get the charge under these peaks baseline corrected, and then we can plot them and we can see that they're not dependent on scan rate. So the charge we measure under the peak isn't dependent on scan rate. That's a good indication that the charge we're measuring here, after doing some data analysis to remove the background, is these are the ions in the thin layer of solution, and we were able to cut out the leakage current, or at least keep it from contributing too much. Here we've also done tests with uranium chloride. This was once again in the borosilicate receptor. We had a small hole this time, and the data is not nearly as good, and there could be a few reasons why. The first is we've been having to synthesize our own uranium chloride. That's why I have the little X here, so we're not sure if it's in a 3+ state or a 4+ state, and we're still figuring out how to get it really pure. So those are some sources of error that we could see here. Other sources of error could be maybe the pinhole was too small, and so we had a large resistance because we don't have as good ion permeation through the glass. We've done some measurements with chromium fluoride and FlyNac. This is with the boronitride receptor. And in this case, you can see that the electrochemistry is a lot more ideal. So your oxidation and reduction peaks are right on top of each other. We have some nice bell-shaped curves. And here's the predicted volume calculated using Faraday's law. And the known concentration of the chromium fluoride we had in there. And you can see that there's noise, but it's consistent. And so we like to see that. We could build out a calibration curve with a bunch of different concentrations and have a good little sensor here. The main challenge that we're experiencing here in our CVs is that this was our first time synthesizing our own FlyNac, making our own FlyNac, and we didn't get the purity right. So there's a fair amount of impurities in this salt. But you can see an interesting theory. You can see flushing and how important flushing is here. We've pushed everything out and we haven't pulled any salt back in with this gray line. And then the black, red, and blue lines show after we've pulled salt inside using our syringe. This is a really nice CV that we took, chromium chloride with a boronitride receptor. And what we get is we have this capacitive envelope, we have these nice bell-shaped curves. They're not right on top of each other, so it's not quite ideal, but it's really quite good. You can also see the effect of flushing here. So these dots, these data points were taken without any flushing. And so you can see there's a trend. We're accumulating chromium chloride inside of our thin layer during these measurements. And then we start flushing with the triangles. And with these triangles, we're introducing more noise in our measurements, but we also no longer have a trend. And we're statistically, we can start to piece together what we know our sample volume to be so that we can get a concentration out of it. This red point here, this data point was taken with chronoamperometry, while the black data points were taken with cyclic voltammetry, measuring the charge under the peaks. We've also done a fairly high concentration. This is actually quite high. 28% chromium chloride, which is around 10 mole %. And it may have been high enough that there were two phases. As I've looked at the data, I think that's fairly likely that there were two phases going on, a chromium chloride rich and a chromium chloride poor phase. We of course need to investigate this more, and we'll probably dial it back and not be so aggressive in the future as we're going after these higher concentrations. But even with these non-idealities, we have some bell-shaped curves, and one of these data points is an outlier. I think we may have been sampling a different phase at this time. But the other two data points agree pretty well with each other, both with our predicted volume and the predicted thickness of our thin layer electrode. So with that, I just want to thank the NUP. They are funding this work, as well as my fellowship that I have through their university program. This work was done in the Pyro Lab at Brigham Young University, which is a great place to work. Can't recommend it highly enough. And I have this little QR code for anyone who'd be interested in making their own thin layer electrode. That'll take you to a Google Doc that has some build instructions. So thank you so much. I hope you enjoy the presentation. And if you have any questions, don't hesitate to reach out.